All right. All right, so we're going to talk about polar form of conic sections today. Kind of bring together all the stuff that we've done in the chapter all in one. So,
are we going full circle?
We're bringing it full circle. All right. That tells me I've been successful in teaching you guys something about math. That you can make good math jokes. All right. So in rectangular coordinates, it's nice. Things work out well. Our equations are nice if we have a conic section if the center is at the origin. So often in rectangular coordinates, we try to put the origin at the center of our conic section. And that makes our equations work out nicely because the h and the k turn out to be 0. So if we have some kind of physical problem that's described by a conic section and we can choose where to put our coordinate system, usually we're going to put the origin at the center. For polar coordinates, things work out really nicely. If we put a focus at the origin, so the origin is at the focus. So all of the conic sections that we talk about today, one of the foci, we're talking about ellipse or hyperbola, is going to be at the origin. For a parabola, the focus is going to be at the origin. So that makes our equations in polar coordinates work out really nicely. So we're going to start with kind of an alternate definition for conic sections. So instead of having a separate definition for each one, we're going to have one definition that takes care of all of them. So we're going to say, so our alternate definition. So we're going to say the locus of points So locus, again, is just some collection that shares a property. So the locus of points such that the distance from a fixed point that fixed point is a focus, and a fixed line, the directrix, is in constant ratio. So that locus, not ratio, is a conic. So any curve where the ratio of the distance from the focus to the ratio to the distance from the directrix is constant is going to be a conic section. And the way we tell which one is which, we have three. We'll just talk about three in this section. If and I say is a constant ratio, and that ratio is the eccentricity. So the eccentricity is the ratio. That is going to give us a conic. And we have three. We're just going to talk about three conics. We're not going to talk about circles with this definition. If E is less than 1, our eccentricity is less than 1, we have an ellipse. So if that ratio is less than 1, we get an ellipse. If E equals 1, the eccentricity equals 1, we have a parabola. And if E is greater than 1, we have a hyperbola. So we can make one definition. The ratio of these distances from the focus to the directrix is constant. We call that constant the eccentricity, and that's going to give us a conic section. And just like before, our eccentricity, if it's less than 1, is an ellipse. If it equals 1, it's a parabola. And if it's greater than 1, it's a hyperbola. So one reason that we do this, it's always nice in math when we can take things that seem like kind of different things and make them just different aspects of one thing. So all of these conic sections are just different aspects of this idea of a locus of points and having to do with a focus and a directrix. So we're just different aspects of that thing. It's always nice when we can bring things, when we can, instead of looking at them as separate concepts, it's just different pieces of one concept. And for all of these, our focus is going to be at the pole. All right, questions so far? The really nice thing about polar form of conics is that there are really only two equations, and they're really kind of almost the same. So our equations. We really only have two, and they're really kind of one. Our equations are going to have the form R equals EP over 1 plus or minus E cosine theta, or R equals EP over 1 plus or minus E sine theta. And what's going to change what type of conic this gives us is E. So we just have these two equations that we have to work with. And sine and cosine are related. They're just, one is just a shift of the other, if we remember when we were graphing them. So it's really one equation. And we also know what kind of symmetry is this form going to have, since it's a cosine function. Cosine functions have polar axis symmetry. So this one will have polar axis symmetry. And since this is a sine function, that's going to have pi over 2 symmetry. So the polar axis symmetry is going to give us a horizontal axis for our conic sections, and pi over 2 symmetry is going to give us a vertical axis. So that's the difference between the cosine and the sine versions of the formula. One that gives us a horizontal axis, the other gives us a vertical axis. And if we're looking, so that's we get all that information just from the form of the equation. And I just wanted to really quickly, when we're talking about the focus and the directrix, so an ellipse, just a quick sketch of an ellipse, the focus is always going to be at the origin. So if we have an ellipse that goes this way, we'd be talking about a shape like that. And the directrix is going to be over here. So it's on the end that's closest to that focus. And for a hyperbola, one focus is at the pole. So if we had a hyperbola that went this way, the directrix is going to be between the hyperbola. It's not right in the center, it's closer to the one with the focus at the pole. So that's where our directrices we're going to lie. All right, so kind of tying things together a little bit. Let's talk quickly about how we're going to use these things, these equations, and then we'll add a little bit more detail. So questions so far? Oh, and I forgot to say one thing. E, just to reiterate, E is the eccentricity. And P is the positive distance from the focus to directrix. So that's the only thing we have to worry about in these equations. We have to worry about the form. That's going to give us our orientation, and the eccentricity, and the distance from the focus to the directrix. All right, we good? So let's look at an example. So we want to find the center the vertices. These are just like the problems that we finished working with rectangular form of conic sections. We're just going to start from a different place. And the foci of, we're going to say this is an ellipse. Given by r equals 15 over 3 minus 2 cosine theta. So this problem tells us this is an ellipse. Well, what do we know right away about this ellipse? Just because of the way this function is written. We have a cosine function, so it has polar axis symmetry. So it's either going to look like this, so it has a horizontal major axis, so it's either going to look like this, or it could go the other way. The long side could go that way. So our ellipse is either going to look like one of those two. Has a horizontal major axis.
E was greater than 1 and it would become a hyperbola.
Oh, we don't know what E is here.
But it's 2.
No, because be careful. Our standard form is EP1 plus or minus cosine or sine theta. So because we don't have a 1 here, it's not a standard form yet. So if we wanted to get a 1 there, what would we do? Divide everything by 3. So we'd have r.
So it's 2/3.
Equals 15.
So it's an ellipse.
Right, 15 thirds
Okay.
over 1 minus 2/3 cosine theta. So E is 2/3, right? But now this came up on the test. Since E is 2/3, does that mean C is 2 and A is 3? No. All right. So we know it's one of these two. How do we figure out which one of these it is?
Positive and negative. Good side of 1.
Well, that's gonna. We'll get to that in just a second. But let's do it a little different way at first. What is theta here? 0. We plug in when theta equals 0. Plug in theta equals 0. R equals 15 over 3 minus 2 times the cosine of 0 is 1. So we get 15. So we get one vertex. That's going to give us a vertex. So we're going to have vertex at 15, 0. And that is in polar coordinates, r theta. Remember, we're in polar coordinates. What is theta over here? Or here? Pi. When theta equals pi, we're going to get another vertex. R equals 15 over 3 minus 2 times cosine of pi, negative 1, which is 15 over 5, which is 3. So we have another vertex at 3 pi. So which one is it going to be? This one or this one? First one, because this is going to be 15, 0, and it's going to be 3 pi. Since this one is bigger, we have to have this one, so we know it's not that. All right, now we have the two vertices. To find the center, the foci, all of that. So we found the vertices. Where's the center going to be? Halfway between the vertices. And we can think of 3 pi. It's easy to get, because this is positive, it's easy to get confused. We can think of this as negative 3, 0 in terms of our rectangular coordinates. So the center is halfway between the vertices, just like before. We're using the same procedure as before. So where's our center going to be? What's halfway between 15, 0 and negative 3, 0? 9, 0? 9, 0? 6, 0, right? So this point over here in polar coordinates is 3 pi, but we can think of this as it's 3 units to the left of the origin. So I'm kind of thinking of it as negative 3 to get my center. Right, right. Because a common mistake is for people to say, oh, it's halfway between 15 and 3 is half of 18, right? Again, you mean just remember that you already have memorized. Yes. All right. Well, so now I have the center. I have the vertices. Can we find, since we have the center, and what else do we know here? One focus is at 0, 0. Always for a polar form of conics. So what is C? C equals 6. This is polar. 6, 0. So 6 units over at the angle of 0. So on the x-axis they're kind of the same. On the positive x-axis at least. So C equals 6. Just like we did with rectangular coordinates, C is still the distance from the center to the focus, because the center is at 6, 0 and one focus is at 0, 0. So where is the other focus? The other focus is at 12, 0. Has to be over here, right? 6 units from the center. That point is that focus is 6 units from the center. That has. Oh, no, sorry. You want to grab the kind of pastel colored ones? Right? So we have the other focus at 12, 0.
Should I just go get this stuff from your office?
I have it here. Thank you. All right, questions there? Isn't this a little easier to work with than rectangular coordinates? It's a little less stuff to do. Questions on what we did there? And remember, these are in polar coordinates. This is r theta. and this is r theta. All right. Well, Jack kind of previewed, kind of saw where we were going with these. He said maybe this plus or minus in our equation tells us something about where the directrix is, and that's exactly right. All right, so we can look at the equation and find the location of the directrix. And this will help us even more when we're solving problems. We will have to do even less work to figure out what our conic section looks like. So if our equation looks like this, R equals EP over 1 plus E sine theta. We know this has what kind of symmetry? Pi over 2 symmetry. So it's going to have a vertical axis. So the directrix is going to have to be horizontal. So we have a horizontal directrix. Because of the sine function, we have a horizontal directrix. And the directrix either has to be above or below the pole, because the pole is the focus. The plus sign tells us it's above the pole. And then if we have R equals EP over 1 minus sine theta, E sine theta, our directrix is going to be below the pole. So not only do we know where our axis is, we know more about the orientation of our conic section. And these two are going to have pi over 2 symmetry. And then for the cosine form of our conics, just like we would think, so if R equals EP over 1 plus E cosine theta, this is going to have polar axis symmetry. So the directrix is going to have to be vertical, perpendicular to the axis. So we're going to have a vertical directrix. And the plus sign tells us it's to the right of the pole. And then that just switches around if we have a minus sign. So it's vertical directrix here, and it's going to be to the left of the pole. And here we have polar axis symmetry. So the form of these equations really gives us almost the entire story about the conic section. All right, so let's look at how we would use all this information to solve a couple more problems. So knowing these facts eliminates a little bit of the work from solving these problems. All right, are we good with this information? Okay. All right, so let's say we want to find the polar equation of the parabola Now, before we write anything else, the polar equation of the parabola. What do we know about the polar equation already? Parabola. E equals 1. So we have one piece one piece that goes into our equation. Polar form of the equation of a parabola. We know E equals 1. The focus is at the pole, always. For polar equations, the polar equations that we're going to use. And the directrix at x equals -4. So let's draw a little sketch. Here's our focus. Here's our directrix. Well, what is this going to be, a sine or a cosine function? Has to be a cosine because it has polar axis symmetry. The focus has to be inside, and the directrix is to the left of the pole. So our form is going to be r equals 1 times p over 1 minus cosine theta. Right? Cosine function because it has polar axis symmetry. This sign is minus because our directrix is to the left of the pole. What's p? Distance from, it's a little different in polar coordinates than before. P is a distance from the directrix to the focus. P is 4. So this tells us that P equals 4. So our equation is R equals 4 over 1 minus cosine theta. And that's the equation of that parabola. Yeah.
So there will always be the 1 minus the second part, or 1 plus or minus.
Mm-hmm. Unless it's written, I just go back to our first example. If we write it like this, if there's not a 1 there, you can always just divide by whatever that number is to get it to be a 1. All right, nice easy parabola there. Parabolas in polar coordinates, parabolas are really easy because eccentricity is 1. All right, let's do one example with a hyperbola, and then I think we'll be set. Questions here? Mm-hmm.
So how do we know that E equals 1?
It's always 1 for a parabola.
Oh, yeah.
That's what makes it a parabola, is that the eccentricity is 1. And if we think back to our original definition of a parabola, we said that the distance from the point on the parabola, from the distance from the focus and the distance to the directrix were equal. If we make a ratio of 2 equal things, we get 1. So, all right. We want the polar equation of the hyperbola with vertices at 1, 3 pi over 2, and 9, 3 pi over 2. So for these kinds of problems, I suggest that we start with a sketch, just like we did with our other kind. So where's the point 1, 3 pi over 2? Down on the vertical axis. So there's one vertex at 1, 3 pi over 2, and there's another vertex at 9, 3 pi over 2. There are vertices. So the hyperbola has, and one focus is at the pole for polar equations. So our hyperbola has to look like, roughly like this. The directrix is in between. So we can write the form of our equation already. So our form is going to be R equals EP over Since it's a vertical axis, we're going to have a sine or a cosine function here. Sine. And since we have directrix below the pole, plus or minus here. Minus. So it's going to have that form. So our job here is to find E and P. And the eccentricity is still, we can think of it, E is C over A. C is the distance from the focus to the center, and A is the distance from the center to the vertices. So we have the vertices. We know one focus is at the pole. We need to find the center. How do we find the center? Halfway between the vertices. So what point is halfway between 1, 3 pi over 2 and 9, 3 pi over 2? 5, 3 pi over 2. The center is at 5, 3 pi over 2. So there's our center here. So now we have all of our information. What is A? From the center to the vertices, what's that distance? 4. From 5 to 1, or from 5 to 9 is 4 units. And C, from the center to the focus? 5. Because the focus is at 0, 0. One focus is at 0, 0. So that's another nice thing about the work that we do with polar equations, conics, is that one focus is always at the pole. All right, so our eccentricity is 5/4. So now we can write R equals (5/4) P over 1 minus 5/4 sine theta. What can we do to this to make our equation look a little nicer? Get rid of those fractions.
1.2.
Multiply top and bottom by 4, right? Multiply everything by 4. So I get R equals, just to make it a little easier to work with, 5p over 4 minus 5 sine theta. A little easy, makes it a little easier to work with. Just multiplied everything by 4. A is a distance from the center to a vertex. C is a distance from the center to a focus. Focus for polar form of conics is always at the origin, always at the pole. Yeah, Jack. Yes. So how do we find P? We've done problems like this before. R and theta are our variables. Do we have an R and a theta value that's on the hyperbola?
Yes.
1 and 3 pi over 2 is an R and a theta that's on the hyperbola. Or 9, 3 pi over 2 is on the hyperbola. So plug in 1, 3 pi over 2, because that's on the hyperbola. Just like we've done in the past when we had an x and a y, and we plug that into the equation to solve for something we need. So we get 1 equals 5p over 4 minus 5 sine 3 pi over 2. So 1 equals 5p over sine 3 pi over 2. What is it? 1, 0, negative 1, square root of 2 over 2, square root of 3 over 2. Which one?
Negative 1.
Negative 1. So we have 4 plus 5, which is 9. So P equals 9/5. So now we can write our equation. Just going to go over here. r equals, plug that back in here, 9/5 times 5, we get 9 over 4 minus 5 sine theta. And there is the equation of our hyperbola. Now, just a quick question. We don't have to go through this, and we talked about it a couple of times really quickly. What if the problem gave you this equation and just said what kind of conic is it? Is it an ellipse, a hyperbola, or a parabola? What would you do? You have to find E. To figure out what E is in this equation, what do we have to do? Divide everything by 4, and we'd see that E is 5/4. We'd write it like this. E is 5/4. And 5/4 is bigger than 1. That tells us it's a hyperbola. All right. Now I have a question for you guys. Why would we want to do this? Why would we want to write our equation of conic in polar coordinates? First off, it's really fun. Yeah, just for fun. But what's an activity? What's not a Friday activity? What's an application where you have a conic section, for example, an ellipse, and something important is at the focus of the ellipse? No. How about the solar system? The orbits of planets are elliptical. The sun is at one focus. It's much easier to describe the orbits of planets using polar coordinates with the sun at a focus. That's the origin of your coordinate system. And you write your equations of your orbits in polar coordinates. So that's one application. Yeah, that's a good question.
Wait, some planets orbit?
Planets orbit in the ellipses.
Why not circles?
What's that?
Is that unique to our solar system?
No.
Most of them do that?
They're always ellipses.
Why is that?
It's just the way the gravity works.
I just want to learn this.
It's because of the way basically the laws of nature work, that it has to be the ellipses. What page are we on? 695.
An hour later? Now. 18. Exact.
Oh, that reminds me. Jacket always matters.
Comes to the coaches.